The beginning of the cosmos represents the greatest challenge to human understanding, straddling the boundary between theoretical physics and deep philosophy. It forces us to suspend everyday notions of cause, duration, and place, because the very vocabulary we use to describe events was itself born in the expansion that followed. All observable reality was compressed into an initial singularity, a point of infinite density and heat, where the laws of nature we know today had not yet held sway. Before that milestone, concepts such as time and space as inherent joint properties did not exist, and our categories of before and after lost their ordinary meaning. Asking what happened before the Big Bang would be as meaningless as trying to walk north from the North Pole. Time simply had no earlier direction, and the question dissolves into the same logical fog that surrounds the singularity itself. The brief interval stretching from instant zero to 100 million trillion trillionths of a second is what we call the Planck Era. At that moment, the observable universe was a tiny sphere with the diameter of a Planck length, about 1.6 x 10 to the power 35 meters, which is 100 trillion times smaller than a proton. Numbers of that size are not intuitive. They mark the edge where our classical imagination stops and quantum gravity must take over. The temperature reached the limit of absolute value, the Planck temperature of 1.4 x 10 to the 32 Kelvin, the point where the wavelength of thermal radiation becomes so short that it reaches the Planck diameter, and nothing can be hotter or smaller, because any attempt to pack more energy into the same region would collapse the description into quantum uncertainty about the geometry itself. Albert Einstein's general relativity, which describes spacetime as a smooth fabric curved by mass, becomes incompatible with quantum mechanics, which governs the realm of probabilities and the infinitely small. Each theory works brilliantly in its own domain, yet here both fail together, and physicists face the uncomfortable fact that our two best maps disagree at the place where the map is needed most. John Archibald Wheeler pictured this epoch as turbulent quantum foam. Because of the uncertainty principle, space-time was not continuous but pixelated, a bubbling texture where microscopic wormholes and quantum black holes appeared and vanished without apparent cause or effect. At the pixel scale of reality, the geometry of the universe was a chaos of violent fluctuations. The search for quantum gravity is the effort to understand this state where gravity, normally dominant on galactic scales, operated under the probabilistic rules of the subatomic world. Understanding this initial singularity is the key to deciphering how the universe works at depth. Just as singularities at the hearts of black holes represent today the natural laboratories where the end of time and the beginning of the cosmos meet. At this stage of colossal energies, nature displayed an algorithmic simplicity that contemporary science desperately tries to recreate in particle accelerators and in equations, always aware that we are reaching toward a regime we cannot fully replicate on Earth. The universe seems to have a clear preference for balanced, symmetric forms because these require far simpler instructions to build, and simplicity at high energy often hides the seeds of the complexity that will appear later as symmetries break. Today, we perceive four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Yet in the extreme heat of the cosmic dawn, those distinctions did not exist, and the world looked in a sense more orderly even while it was hotter and more violent. So it was under the rule of the electroweak force, where electromagnetism, the weak force, and the strong force were one unified interaction. The decision about each force's identity, that is, which side of the coin would land face up, was only reached as the initial energy began to run out. As the universe expanded and cooled, the disk lost its spin and came to rest, breaking the original symmetry and forcing the forces to take on distinct identities. The Grand Unification epoch was a setting where the distinction between light and matter did not exist. Extremely high-energy photons turned spontaneously into matter-antimatter pairs, maintaining a steady flow of creation and annihilation. X-gauge bosons mediated interactions, allowing quarks to turn into leptons in ceaseless metamorphosis. Although the cosmos was smaller than an atom, it held the energetic potential of all the galaxies that would ever exist. A temperature of 100 quadrillion degrees kept reality in a state of near-perfect symmetry, but that stability was temporary. When the cosmic clock reached 1/1,000,000,000 of a trillionth of a trillionth of a second, the strong force split from the others, triggering an event that would change the scale of the universe forever. This concept describes a sudden period of exponential growth that fixes fundamental flaws in the traditional model, such as the horizon problem and the flatness problem, and it changed how cosmologists picture the first instance from a simple fireball into a dynamical episode with its own internal machinery. The horizon problem asks how opposite regions of the universe, separated by billions of light-years, share the same temperature of 2.7 Kelvin. Without inflation, those regions would never have had time to exchange heat, and the cosmic microwave background's remarkable uniformity would be an unexplained coincidence rather than a clue. Inflation explains that the universe began tiny and in thermal equilibrium before being violently stretched, spreading that uniformity across all observable space. Flatness refers to the geometry of the cosmos, which appears perfectly flat. Inflation stretched the fabric of space so that any original curvature became imperceptible, like the surface of a balloon inflated to the size of a galaxy, which would look flat to any local observer. Alan Guth proposed that the universe underwent about 90 doublings in less than a trillionth of a second. That event turned a subatomic point into a structure larger than the Virgo supercluster of galaxies. Unification theories suggest the early universe should have been full of particles with only one magnetic pole, but inflation diluted them so much that statistically only one monopole would remain per observable universe. Beyond solving those puzzles, inflation acted as a cosmic amplifier. The microscopic quantum fluctuations of the original foam were stretched into large-scale density irregularities, the gravitational seeds that would later collapse to form the first stars and galaxies. When the inflation engine stopped, the energy in the inflation field did not vanish. It decayed and was dumped into space in a process called reheating. That was when the universe became a seething soup of particles and radiation, but one essential piece was still missing: mass. Until then, all particles traveled at the speed of light, unable to clump or form structures, which means the universe could store energy and charge, but could not yet build the slow, sticky chemistry that makes worlds. Mass was granted through interaction with the Higgs Field, an invisible entity, permeating the entire fabric of spacetime, present everywhere, yet revealed only indirectly through the properties of the particles that couple to it. If an unknown, unimportant person crosses the room, they do so without resistance, because no one clusters around them. That person is like the photon, a massless particle that moves freely. If, however, an extremely popular, famous figure enters, guests immediately crowd around them, slowing their motion. The resistance that person feels when trying to move through the crowd is what we perceive as mass. Different particles feel that resistance differently. The electron interacts lightly, while the top quark is heavily surrounded by the crowd, becoming very heavy. That displacement of information in the field is the boson, whose discovery in 2012 at the Large Hadron Collider confirmed that mass is not an intrinsic property of matter, but the result of constant interaction with the vacuum. Without the Higgs field, the universe would be a sea of eternally fast particles, and gravity would never have had the power to organize the cosmos into atoms and worlds. The structure of matter is catalogued by the Standard Model, which organizes the 12 fundamental particles. They divide into quarks and leptons. There are 6 kinds of quarks, known as flavors: up, down, strange, charm, top, and bottom. The leptons include the electron, the muon, and the tau and their respective neutrino varieties. Protons and neutrons are hadrons, composite particles that formed when the universe cooled enough for the strong force to confine quarks. A proton is the union of 2 up quarks and 1 down quark, while a neutron is 2 down quarks and 1 up. Yet, the source of these particles' mass is counterintuitive. The individual quark masses add up to only 9% of the proton's total mass. The remaining 91% does not come from physical substances, but from latent binding energy and the frantic interactions of gluons, the messengers of the strong nuclear force. According to Einstein's equation, that immense energy shows up as most of the mass of every atom in our bodies. That prevents quarks from existing freely in nature, a phenomenon known as confinement. In the first microseconds, the universe was a quark-gluon plasma, a state of matter so dense and hot that quarks flowed freely before being locked forever inside atomic nuclei. The reign of quarks and leptons supplied the basic architecture of matter, ensuring the universe ceased to be only a flow of radiation and became a laboratory of chemical construction. A staggering mystery hangs over our existence: the asymmetry between matter and antimatter. In 1928, Paul Dirac predicted mathematically that for every matter particle there should be an opposite charge counterpart. which was confirmed in 1932 by Carl Anderson with the discovery of the positron. The elegance of the prediction made the later cosmological problem even sharper. If symmetry is a guiding theme, why did the universe keep a leftover of only one kind? In theory, the Big Bang should have produced equal amounts of both, because matter and antimatter annihilate instantly on contact, turning mass into pure energy. The universe should have become an absolute void filled only with light, leaving behind no stars, planets, or people to argue about the paradox. Yet there was a fundamental symmetry break. For every billion matter-antimatter pairs that annihilated each other, only one excess matter particle remained. That 1 billionth residue is what composes all the stars and galaxies we see today. The cause of that small instability in the laws of nature, known as parity violation, suggests that the rules of physics do not treat matter and its mirror image identically. Experiments by Chien-Shiung Wu showed that the weak force favors certain directions of interaction, breaking the perfection one might expect from the cosmos. Our existence is direct testimony to that statistical error in the Great Annihilation. We are made from the ashes of a survival war where matter prevailed by 1 part in a billion. This is the universe's first episode of nuclear physics written large, before stars existed, yet already setting the elemental baseline for everything that followed. With the temperature falling to 1 billion degrees, the cosmos was cool enough for protons and neutrons to join without being immediately destroyed by radiation bombardment. The final particle ratio was decided by a subtle difference. The neutron is slightly heavier than the proton, and small mass gaps can swing cosmic outcomes when thermodynamics pushes the system one way or another. In the early heat, they constantly swapped identity, but as cooling advanced, the energetic path to become a proton was easier than the reverse. That yielded a ratio of 7 protons for every neutron. In that fusion process, nuclei of hydrogen, helium, and traces of lithium were created. The observed abundance of 75% hydrogen and 25% helium is among the strongest evidence for the Big Bang, because theoretical calculations of primordial nucleosynthesis match perfectly what telescopes see today in the depths of space. If the neutron were only a little lighter than the proton, all chemistry would be impossible, because the universe would be an inert sea of uncharged neutrons. The precision of that mass difference allowed hydrogen to remain stable, guaranteeing fuel for future stars that forged the complex elements of biology. As Brian Cox described, Earth is today the only island of meaning in an ocean of 400 billion suns within the Milky Way. If we destroy this small stage, we may destroy meaning across the entire galaxy forever. We are a temporary pattern of atoms that emerged from an impossible singularity to observe the cosmos. That pale blue dot of matter, survivor of brutal annihilation, now bears the responsibility of understanding its own origin. The story that began in a point smaller than an atom now shows up in human curiosity, seeking to grasp how light became life. Till x 10^44 seconds after the beginning of everything, the universe's temperature reached about 1.4 x 10^32 Kelvin, the so-called absolute heat, source 2, a scale where thermal motion and quantum uncertainty merge into a single obstacle to intuition. At that magnitude scale, the Planck distance, estimated at 1.6 10^35 meters, marks the limit where quantum fluctuations make the very geometry of space and time unrecognizable. Source 2. Before that milestone, the 4 fundamental forces of nature, gravity, the strong force, the weak force, and electromagnetism, operate as one unified force, in a state of symmetry that contemporary science still seeks to describe through a theory of quantum gravity. Source 2. The universe at that moment consisted of bubbling, dynamic quantum foam, where microscopic black holes and wormholes appeared and vanished spontaneously, challenging linear causality. Source 2. As the universe expanded and cooled, the first major symmetry break occurred, separating gravity from the other 3 quantized forces, which remained united in what we call the electroweak force, source 2. That period, known as the Grand Unification Epoch, was dominated by processes so energetic that photons turned spontaneously into matter-antimatter pairs, such as quarks and leptons, which annihilated and returned to a radiation state in negligible time fractions, source 2. To explain the thermal homogeneity and flat geometry we observe today, cosmic inflation theory, proposed by Alan Guth, postulates exponential expansion occurring in less than a trillionth of a second, source 2. The proposal is powerful because it ties together several unrelated-looking puzzles with one dynamical story, rather than ad hoc assumptions for each observation separately. During that event, the universe doubled in size roughly 90 times, growth so vast that, applied to a sheet of paper 1/10 of a millimeter thick, it would yield a thickness greater than the Virgo supercluster, spanning 130 million light-years. Source 2. A thought experiment that makes the expansion feel less abstract and more violently concrete. Inflation solves the horizon problem, explaining why opposite regions of the sky have identical temperatures of 2.7 Kelvin. Even though they are separated by distances, light could not traverse to balance heat. Source 2. It also solves the flatness problem, smoothing any initial spacetime curvature until it looks perfectly flat to internal observers. Source 2. Another critical solution from this process is dilution of magnetic monopoles, which would have been abundant in a dense, primitive universe, but were spread by expansion until only one per observable universe remained. Source 2. The density quantum fluctuations that occurred on microscopic scales during this period were amplified by inflation, becoming gravitational seeds for future galaxy and cluster formation. Source 2. At the end of that accelerated expansion, the energy field responsible for inflation decayed, pouring its energy back into space in a process called reheating, decisively giving rise to matter and radiation. Source 2. With subsequent cooling, the universe entered the electroweak era, where the electroweak force split into the strong force and the electroweak force. Source 2. Each split is a chapter heading in cosmic history because forces are not merely labels, but the rules that determine what kinds of structures can exist later. At that stage, particles still lacked mass and traveled at the speed of light until, about a trillionth of a second after the start, the Higgs Field appeared. Source 2, switching the universe from a fast, symmetric spray into a medium where persistence and inertia become possible. The manifestation of that field and its messenger boson allowed particles such as quarks and leptons to acquire mass through interaction with this energetic field, permeating all spacetime. Source 2. A useful analogy is a popular figure entering a crowded party. The attention they draw from people around them hinders their motion, giving inertia analogous to mass. Source 2. Discovery of the Higgs boson in 2012 at the Large Hadron Collider confirmed the validity of this mechanism and the standard model of particle physics, which describes 12 fundamental matter particles and 4 force bosons. Source 2. It is notable that most of a proton's mass does not come directly from its quarks masses, which are only 9% of the total, but from energy stored in gluon interactions inside the atomic nucleus, per Einstein's mass-energy equivalence. Source 2. Discussions of fine-tuning are not mysticism, they are honest bookkeeping about how narrow many parameter ranges appear when we ask for atoms, chemistry, and long-lived structures. If gravity were slightly weaker, the cosmos would be only a thin cloud of hydrogen gas. If stronger, all matter would collapse into premature black holes, blocking star and planet formation. Source 2. And either failure mode removes the stage on which complexity could later emerge. The balance between protons and neutrons, established around 1 second after the start, yielded a 7-to-1 ratio, favored by the slight mass difference between up and down quarks. Source 2. That excess of charged protons allowed future chemistry and biology because excess neutrons would have produced a universe composed mostly of inert helium. Source 2. In parallel came matter's triumph over antimatter. Although created in nearly equal amounts, a tiny asymmetry let one matter particle survive per billion annihilations. Source 2. That fortuitous survival is why the observable universe contains physical structures instead of only a sea of gamma radiation. Source 2. That transition is sometimes described quietly, yet it is one of the great phase changes in history. The universe becomes a place where light can carry information across distance without being endlessly knocked around. Before that, the universe was opaque plasma, where photons were constantly scattered by free electrons, 197-1999. With the formation of the first hydrogen and helium atoms, space became transparent, allowing light to travel freely for the first time, 190-193, releasing the cosmic microwave background that still surrounds us as an ancient photograph of the young cosmos. That primordial light is still detected today as the cosmic microwave background, providing an image of the universe in its infancy and the strongest evidence for a hot, dense initial state, 197-199. Small density variations detected in that radiation show how dark matter began to form the gravitational scaffolding that would draw gas to create the first stars, 200, 201, 208, 213. Baryon acoustic oscillations, density waves propagating in primordial plasma, left imprints that shaped large-scale galaxy distribution, visible in the structure we now call the cosmic web, 200, 201, 208, 213. The study of extreme gravity leads us to black hole physics, whose theoretical concepts trace to the work of John Michel and Pierre-Simon Laplace in the 18th century, 1-15. Their work is a reminder that some ideas arrive early, even when the mathematical language needed to complete them has not yet been invented. They imagined stars so massive that escape velocity would exceed the speed of light, making them invisible to the outside world. 1-15. A conclusion that follows Newtonian reasoning to its extreme, even if it cannot capture the full relativistic story. Yet it was Carl Schwarzschild who in 1916 derived the exact solution to Einstein's equations, describing the event horizon of a static black hole, 1-15. The event horizon is not a solid surface, but a boundary from which no information or light can escape because of infinite space-time curvature, 1-15. To an external observer, time for an object falling toward the horizon appears to slow until it freezes completely at the black hole's edge, 1-15. For a freely falling astronaut, the experience is of normal time when crossing that boundary, underscoring the relative nature of time in general relativity, 1-15. Inside the black hole, relativity predicts a singularity, which should not be understood as a place in space, but as a moment in time marking the end of every time-like trajectory, 1-15. The result was shocking because it connected thermodynamics, quantum fields and gravity in a region where intuition had long been unreliable. This phenomenon arises from the creation of virtual particle pairs in the vacuum near the horizon. When one particle falls into the black hole and the other escapes, the object loses mass and eventually evaporates over eons, 16-25, turning eternal black holes into long-lived but not necessarily permanent objects within quantum gravity. That discovery generated the information paradox, because if a black hole evaporates and vanishes, all information about matter that fell into it seems destroyed, which would violate quantum mechanics laws requiring information conservation, 16-25. Debate among Hawking, Leonard Susskind and Gerard 't Hooft was intense, with Susskind arguing information must be encoded on the black hole's surface holographically, 16-25. Indeed, Jacob Bekenstein observed that a black hole's entropy is proportional to its surface area in Planck units, not its volume, suggesting a three-dimensional description of a region can be fully contained on its two-dimensional boundary, 26-45. Contemporary physics suggests space and time are not fundamental elements, but emergent properties arising from quantum entanglement, 26-45. The geometry of the universe would therefore be a manifestation of how quantum information is connected, 26-45. Curiously, how the universe protects that information at event horizons resembles quantum error-correcting codes developed for advanced quantum computing, 26-45. This obeys the no-cloning theorem, which forbids identical copying of quantum states, forcing nature to store data redundantly and robustly to preserve the fabric of reality's integrity, 26-45. Today, tools like the James Webb Space Telescope let us watch early galaxy formation only 200 million years after the start, revealing structures more organized than models predicted and forcing revision of our theories of galactic growth, Source 2. Meanwhile, gravitational wave astronomy, through interferometers such as LIGO and Virgo, detects black hole collisions billions of light-years away, measuring ripples in the space-time fabric and confirming relativity's predictions in extreme energy regimes, 1-15. Direct observation of supermassive black holes, such as the 6 billion solar mass one in galaxy M87 and Sagittarius AB at the Milky Way's center, shows these objects are not mere mathematical abstractions, but fundamental components of cosmic architecture, 1-15. The tension is not merely poetic. It is a clash between enormous opportunity and an observational emptiness that has persisted despite generations of searching. Cosmic silence may be explained by the rare Earth hypothesis, which suggests the long 4 billion-year stability required for intelligent life's evolution is an exceptionally rare phenomenon. Brian Cox interview, a claim that does not rule out life elsewhere, but raises the bar for what elsewhere must accomplish to mirror our path. Factors such as solar stability, absence of nearby supernovae, and protection against catastrophic impacts allowed an unbroken chain of life from cell to civilization, Brian Cox interview. That biological rarity, combined with the complexity of eukaryotic cell emergence, may mean we are the only civilization in our galaxy, giving us immense responsibility to preserve meaning and knowledge. Brian Cox interview. Understanding the universe as a quantum information processing system places us as observers who not only witness reality, but are part of the entanglement network that sustains it. 26-45. If time and space emerge from underlying layers of information, the Big Bang can be seen not only as an explosion, but as the start of cosmic processing, whose fundamental laws we are only beginning to decipher. Source 2. Hawking radiation, though faint, carries secrets of matter evaporation and possible reconstruction of cosmic history from data gathered on timescales of 10 or 120 years, 16-25. Even if black holes look destructive, they are natural laboratories where nature reveals its deepest secrets, from the nature of mass to quantum information redundancy. 26-45. Theoretical cosmology teaches that from recombination's cosmic transparency to holographic reality's limits, there is a logical mathematical continuity linking the infinitely small to the infinitely large. 190-193, 26-45. The journey of human knowledge, which began with observing starlight, now turns to gravitational waves and quantum entanglement as keys to understanding the universal engine. 115. What changes across centuries is not curiosity, but instrumentation. We still ask what the world is made of, yet we can now test answers in regimes our ancestors could not even define precisely. Each new discovery, whether inside a particle accelerator or in intergalactic depths, reinforces the idea that the universe is comprehensible and structured by universal laws. Source 2. Even when those laws lead to conclusions that feel alien to daily experience. Our solar system's stability and biological evolution result from a chain of events that began with inflation and was shaped by dark matter and Higgs energy. Source 2. Looking ahead, resolving the information paradox and understanding singularities will be milestones letting us judge whether the universe is eternal or had an absolute beginning in time. Source 2, 16-25. For now, we remain on our pale blue dot, studying gravitational abysses and primordial light to understand our place in the vast tapestry of matter and information we call reality. Source 2. The transition between Schwarzschild's classical physics and Mulder-Seena's modern view shows how our perception of reality shifted from a fixed geometric stage to a dynamic system of emergent information. 1-15, 26-45. Human consciousness and the ability to frame these questions are themselves part of the phenomenon we try to describe, where temporary patterns of atoms organized in complex brains seek the origin of consciousness and of nature's laws. Brian Cox interview. The search for answers about life's probability and the initial singularity's nature continues to drive technology and philosophy, uniting them in a continuous narrative of exploration. Source 2. The clarity reached 380,000 years after the start lets us today see the past and plan the future, using particle physics and relativity knowledge to test the limits of the possible. 197, 1999. Each background radiation photon and each bit of information on a black hole horizon are pieces of one cosmic puzzle humanity is dedicated to solving. 1625, 197, 1999. The inflaton field's role in creating large structures and dark matter's role in maintaining them show the visible is only a fraction of underlying reality. Source 2, 200, 201. Black hole physics, challenging our notions of volume and information, points toward a revolution where the three-dimensionality we perceive is only a projection of two-dimensional data. 26-45. That holographic view does not diminish the cosmos's importance, but reveals mathematical depth that makes reality still more fascinating. 26-45. As observational instruments grow more sensitive, we approach the moment when we may detect gravitational waves from inflation itself, opening a window to the Planck era's first instance. 1-15 Source 2. The final understanding that spacetime is woven from quantum entanglement and that information is existence's basic unit unifies physics in a coherent structure. 26-45. Black holes, far from being mere matter sinks, are pillars where physical laws meet, and where Big Bang secrets are stored, 1:15-1625, information preservation and error protection on cosmic scales ensure nature's laws stay consistent across billions of years, 2645. This scientific narrative, linking light from first recombination to extreme singularities, is humanity's story of seeking truth in a universe that, though vast and silent, reveals relentless logic to those who persist in decoding its signals. Source 2, 1-15. Our eyes and ears evolved for survival on a planet, not for reading spacetime curvature or quantum correlations at cosmological scales. So strangeness is not an accident, but an expected consequence of the scale mismatch. At the center of that mystery stand black holes, objects that for decades were treated only as mathematical curiosities or theoretical nightmares of stubborn physicists. Today we understand these titans are not only real, but fundamental to cosmic architecture. The idea of something so dense that not even light could escape its gravitational pull is not a modern invention. As early as the 1780s, brilliant minds such as English clergyman John Michel and French mathematician Pierre-Simon Laplace independently imagined what they called dark stars. They grounded the concept in escape velocity, the speed any object must reach to break free of a celestial body's gravity. On Earth, that speed is about 11 kilometers per second. For the Sun, the value jumps to more than 600 kilometers per second. Michel and Laplace pictured stars so massive that escape velocity would exceed the speed of light itself, making them invisible to human eyes. Laplace wrote poetically that the universe's largest bodies might remain invisible because of their very magnitude, a striking insight for someone who lived centuries before Einstein. Although the Michel-Laplace model rested on Newtonian physics and was therefore incomplete, it paved the way for the revolution brought by general relativity in 1915. Albert Einstein described gravity not as a mystical force acting at a distance, but as distortion in the fabric of spacetime itself. Soon after, physicist Karl Schwarzschild found the first exact solution to Einstein's equations while serving in World War I. Schwarzschild described mathematically what happens to space and time around a perfectly spherical static star. He discovered that if you compress matter enough, space-time curves so sharply it creates a region of no return. To grasp that compression scale, to turn Earth into a black hole, you would have to crush all its mass into a sphere only 1 centimeter in radius. For the Sun, it would need to shrink to a sphere about 3 kilometers across. For much of the 20th century, many physicists, including Einstein himself and respected Arthur Eddington, doubted nature would allow such absurdities. Eddington even declared nature should forbid such a great anomaly. Yet the universe does not share our ethical or aesthetic hesitations. Most arise from the collapse of massive stars, at least 3 or 4 times the Sun's mass, that exhaust their nuclear fuel and succumb to their own gravity. But even larger giants exist. Nearly every galaxy harbors a supermassive black hole in its core. The monster at the center of Galaxy M87, captured in a historic image by the Event Horizon Telescope collaboration, has 6 billion times the Sun's mass and lies 55 million light-years away. At the heart of our own Milky Way lies Sagittarius A, a slightly more modest yet still staggering giant with 4 million solar masses. These objects are gravitational anchors helping shape galaxy evolution, influencing star formation and matter distribution on cosmic scales. Their existence was dramatically confirmed by gravitational wave detection, ripples in the space-time fabric crossing the universe. Physicist Kip Thorne described these waves as a storm in space-time itself. Observatories such as LIGO and Virgo use laser interferometers with 4-kilometer arms to measure shifts as small as a fraction of an atomic nucleus. That technology let us hear collisions between black holes and neutron stars, revealing a universe far more turbulent than we imagined. Surprisingly, detected collisions often involve black holes 30 to 40 times the Sun's mass, an abundance that challenged astronomers' early forecasts. As we approach the event horizon, the boundary from which nothing escapes, classical physics begins to fail, and we are forced to reconcile general relativity with quantum mechanics. The horizon is not a material membrane you could touch. It is a property of the causal structure. Yet it becomes the place where quantum effects can no longer be ignored if we want a consistent story. Stephen Hawking changed our view of these objects in the 1970s by showing black holes are not completely black. Applying quantum theory near the event horizon, Hawking proposed they emit a form of radiation. The mechanism can be pictured as virtual particle pairs constantly arising from the vacuum. Normally, those particles annihilate instantly, but at a black hole's edge, one particle can fall in while the other escapes to the universe. That process removes energy and mass from the black hole, making it shrink and eventually evaporate after eons. That discovery spawned the information paradox. If a black hole evaporates completely, what happens to all information about what fell into it? In fundamental physics, information must be conserved. If you burn a book in a furnace, or destroy it in a nuclear blast, physical law says that if you collect every atom and every resulting photon, you could in principle reconstruct the original book. Yet Hawking's early calculations suggested black holes worked like cosmic erasers, destroying information forever. Resolving the paradox seems to lie in the holographic principle, an idea emerging from Jacob Bekenstein's work. He noted that the amount of information a black hole can store does not depend on its volume, but on its event horizon surface area measured in Planck units. The Planck unit is the smallest distance that makes sense in physics, far smaller than a proton. To illustrate the strangeness, imagine a library. Intuitively, we would think how much information it holds depends on how many books fit in its interior volume. But black holes tell us information is limited by the wall's surface area. That suggests our three-dimensional reality may be a projection of a two-dimensional boundary, analogous to a hologram where a two-dimensional film holds all data to project a three-dimensional image. Juan Maldacena expanded this with correspondence between gravity in a space and a quantum theory on its boundary. That view suggests space and time may not be fundamental, but emergent properties of something deeper, such as quantum entanglement. On that theoretical frontier, nature seems to use quantum error-correcting codes, similar to those we try to build for modern quantum computers, to store reality redundantly and robustly. Fermi's paradox poses a simple, troubling question. If the Milky Way has 400 billion stars and most host planets, where is everyone? With 10 billion years of history, there was ample time for civilizations to arise and colonize the entire galaxy. Even with today's rocket technology, self-replicating machines known as von Neumann probes could spread across the galaxy in about 100 million years, a blink in cosmic terms. Yet we see no signs of vast stellar engineering or interstellar communications. The Great Silence may have many explanations. One is the dark forest hypothesis, suggesting civilizations stay hidden for fear of cosmic predators. Another is the Prime Directive, a moral choice by advanced civilizations not to interfere with less evolved worlds. But perhaps the answer is more biological and statistical. Frank Drake, who formulated the famous equation to estimate civilization counts, used the orchid analogy to explain loneliness. A rare orchid may bloom only 1 or 2 days, then vanish. Perhaps civilizations are like those flowers, blooming and dying at different moments, never crossing in time and space. Life on Earth has lasted nearly 4 billion years, maintaining a continuous unbroken chain, despite living in a violent universe. We were lucky not to be hit by a nearby supernova or an asteroid large enough to sterilize the planet throughout that time. Moreover, biology faces extreme evolutionary bottlenecks. For most of Earth's history, life consisted only of simple cells. What we call the freak encounter hypothesis was needed, a unique event about 2 billion years ago when one simple cell swallowed another, giving rise to the complex eukaryotic cell. That event may be so rare, it happens on only a handful of planets in the entire universe. This is the great filter concept, an obstacle so hard to overcome it stops life from leaving its infancy. The filter may lie in our biological past or our technological future. If the filter lies ahead, it may appear as nuclear or biological self-destruction or failure to manage artificial intelligence before we become a multi-planet species. Our political wisdom often seems to lag our technological power, making the future an uncertain crossing. The hard problem of consciousness asks how a temporary pattern of atoms, organized by evolution, can give rise to subjective feeling of being, and it sits oddly alongside the crisp precision of physics. Two kinds of mystery in one species. We are made of stardust that can now think about stars. That consciousness lets us investigate nature's laws and notice the universe's fine-tuning. There are physical constants, such as the fine structure constant, roughly 137, that set electromagnetic interaction strength. If that value were slightly different, atoms would not be stable, stars would not shine, and life's chemistry would be impossible. That leads us to ask whether our universe is unique or we are part of a vast multiverse where only regions with the right laws can be observed by intelligent beings. Those questions take us back to the beginning, to the Big Bang singularity 13.8 billion years ago. The physics we study in black holes is the same needed to understand the universe's birth. At the start, during the so-called Planck Era, the universe was so small and dense that space-time itself was bubbling quantum foam of microscopic black holes and spaceworms. At that moment, the four fundamental forces of nature, gravity, the strong force, the weak force, and electromagnetism, were united in one primordial force. But if a famous figure enters, everyone clusters around them, hindering their motion and giving them, in a sense, resistance or mass. It is that interaction with the Higgs field that allowed atoms, and eventually us, to form. Understanding that origin is essential to know whether time had an absolute beginning, or the universe undergoes eternal cycles of expansion and contraction in one great cosmic leap. That entire vast journey of knowledge, from a black hole's infinite density to time's origins, returns us to humility and responsibility. The image is scientifically modest and emotionally enormous at once, because it compresses history into a single frame without pretending the universe is small, only that our stage is. Brian Cox reinforced this by suggesting Earth may be the only island of meaning in an ocean of hundreds of billions of suns. If so, the moral weight of our choices rises with the cosmic stakes, not because the cosmos cares, but because we might be rare witnesses in a mostly empty auditorium. If intelligence and consciousness are such rare, fragile phenomena, our species' survival ceases to be mere self-preservation and becomes a cosmic imperative. We are the form the universe found to contemplate itself, to measure its own constants, and to admire its own beauty. Extinction of human consciousness would therefore be a tragedy of universal scale, because meaning exists only where someone perceives it. Our duty is to protect this pale blue dot, treating one another with greater kindness and preserving intelligence as the light that illuminates the vast, silent darkness of the final horizon. That duty is not sentimental decoration added after the equations. It is the practical conclusion of a story in which knowledge is fragile, civilization is recent, and the universe will continue indifferently whether we thrive or fail. If we take the cosmic perspective seriously, stewardship becomes less like a slogan and more like a consequence of what we have learned about rarity, contingency, and the narrow pathways that allow matter to wake up and understand itself. The story does not end with awe. It ends with what we choose to do with the interval in which the universe can speak through us.